Hi, I'm Steve Simske. I'm a professor here in the Systems Engineering Department at Colorado State University. My research areas are pretty broad because I've had a lot of chance to participate in various things. So cybersecurity, analytics, signal processing, image processing, and sensing are the main ones that I work on here.
Hi everyone, I'm Dan Herber, assistant professor at Systems Engineering at Colorado State University. I do a lot of work in design, and particularly design challenges for lots of big systems, and doing this with model-based system engineering, design optimization, architecture synthesis, and controls and dynamics. There's a lot of interesting design questions, and applying these to things like energy systems, defense systems, things along those lines.
Thanks. So for my research up till 2035, you notice they've given up on 2020. Everybody's like, oh, it's 2020 vision is what led to 2020, and that ended up being kind of the worst year ever. So 2035 is probably going to be a lot better, and I'm looking forward to that as systems engineering is kind of becomes to engineering what chemistry is to science. It becomes the central engineering. And all of those big things that we need to be able to build across all of the mechatronics, all of the chemistry, all of the physics, all of the different aspects of any large system, things like sustainability, safety, cybersecurity, data analytics, those are going to be the big areas, and figuring out how to make those work with those multiple systems, that's definitely where I'm interested in going. How about you, Dan?
Yeah, so in my space, I see as systems become more complex, and there's more and more decisions that need to be made, more and more things you need to account for. So I foresee really that there's going to be a large push for developing the methods and tools to actually manage and navigate that wide space of decisions and choices that modern system engineers are going to have to wade through. And along those lines is going to be communication with others, and developing a more robust methodology to handle the complexity of the modern systems.
So one of the areas that I think is really important about where systems engineering fits into the future, and where some of my research, and certainly tied to some of yours, is going to fit in, is figuring out how to make all of these components work together safely and securely. One of the issues we have right now, if you look at it, you walk into a new car, it knows who you are, your phone is instantly connected to the car, all of your information is downloaded onto that car. How do we know that car has the same type of cybersecurity or cyber-physical security in the case of a car as everything else that you're trusting does? Your data is going everywhere. People don't know where the data is going to end up. We need some types of systems level analytics and security to basically figure out where that data is gone, why it's gone there, and what we can do to keep it safe where it's gone. So things like dual factor authentication are a great on-ramp for that, but figuring out ways to actually put in situ encryption in place and be able to make those systems work together without losing all of the expediency by having to decrypt everything on the fly is going to be a big part of systems engineering, I feel, going forward.
Yeah, so I think for really systems engineering to have the impact we want it to have at the systems level on these large complex systems, we need to kind of rethink how we approach modeling and how we approach interconnecting the systems as early as possible in the system design process. And for me, the main area of my research and where I see a lot of progress being made now and where I see it going in the future is with model-based system engineering, where we kind of fundamentally rethink how we represent a system. We think about it in terms of these key principles that MBSE helps us capture, enable, formalize. It allows us to really build a true systems perspective on what the system is and what it should be, and make decisions with that information available. And yeah,
I actually really like that approach, because we talk to our students in analytics, certainly in cybersecurity, in sustainability, in safety, all these broad systems issues, as it's really hard to retrofit. And it's 10 to 100 times more effective to actually build that into the system from the ground up. The model-based systems engineering that you're talking about really complements the types of designs and analytics that I'm trying to get my students to use for these broad concepts and for these broad technologies that actually go across all of the engineering and scientific disciplines. It's really cool to hear.
Yeah, and the ability to design a system that can be resilient, adapt to change, adapt to different technologies, adapt to new data inputs, because the system is developed in a way that perhaps we didn't expect. Bringing in those velocities are a little bit easier, I feel, when we have centralized model representation or just a more clear understanding of what the system should be, how it should be designed. So it's not just doing engineering the way we've done before, but when we have these mechanisms to make a more resilient design, a more robust design, we can actually enable systems to work as we want in this complex world.
That's really important. And one of the things that we do in both my analytics and my cybersecurity research is we look for design patterns, a set of tools that we can reuse, repurpose, even though the specifics are going to be different. It sounds to me like that harmonizes really well with the model-based systems engineering work that you're leading.
Yeah, the idea of there's design patterns, and we kind of scale them up sometimes to reference architectures. It's an application of an entire piece of the architecture picture, which includes maybe a collection of design patterns. It may include existing data from previous design development activities. All that can feed into reuse and making designs that are proven, that are built into the next generation of systems that we're doing. Continuously learning, continuously developing towards better systems. Having this model-centric perspective, or even just a model and data-centric perspective, can really enable reuse and application of things that we know are good.
Yeah, I love that. So it's modularity, repurposability, and being productive from the first day you start working on a project. I wish I could say that about my past.
For some of this comes from the MBSE perspective, but I also think it is in a lot of domains where we can in classes we can more straightforwardly teach the technical concepts. We can teach what we should it's harder to teach what we should be doing. It's more of the the philosophy behind what's the right systems perspective to apply these tools. In MBSE, I can teach what a system L diagram is and try to give a lot of examples, but that next step of how do you actually take that methodology and apply it to a new system, something that hasn't been modeled before, that has a lot of questions. So I think that the systems thinking perspectives and the philosophy that these are tools to help us do better systems engineering is what I like to see incorporated more into the curriculums, what I try to incorporate into the MBSE courses, into the optimization courses. Optimization is just a tool to answer a question of, how things should be done in an optimal or a good way. But, you need to know that the answer you're getting out is what you want, essentially, from that progress. So teaching that, more fundamental, how should we be doing things, rather than, the technical tools is how I see a lot of the system engineering courses evolving over time, case studies and insights being really brought into the classroom.
I like that approach, and I think it harmonizes or syncs really well with the type of things that I'm doing in my classes and that I see us needing as a discipline, as a systems engineering discipline, which is really what we're talking about here. And when you look at the way to discipline yourself to make systems better, you have to think across all of the different subsystems, and you have to say, wait, the tools that are there are going to change, right? We don't use the same hammers we used 100 years ago. They were little tack hammers. I don't even know what people, dunk, 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 putting stuff up. We use different hammers now. Drills are, power drills now. They used to be, a little hand turning drill or whatever 100 years ago. So teaching people how to think and how to figure out how to assimilate all the different tools into their courses, I think is a big deal. And, if you look at a graduate program like ours in systems engineering, we assume that the students have some background and that they're familiar with some of the tools, or they can make themselves familiar, right? So to differentiate as an educator, one of the things we're definitely trying to do is, like you said, to cross over, give those case studies, talk about what happens in a productive environment. I've been in environments where we had to ship 9 different versions of a printer or a scanner or a copier in a year. And I'd have a stack of these all the way up to the ceiling. And it's like, if I had a one-off type of mentality for that, I'd have quit or lost my job within a couple of months, because I'd have missed 2 or 3 shipments and that would be the end of it. So I really like what you're saying there. And I think the case study and being able to dive deep with something and be somewhat agnostic to the tools. I mean, I'm fairly agnostic to the tools, whether the student is familiar with R or Python or Java or C# or whatever else they choose to use in my classes. I'm okay with that. Puts a little more onus on us as teachers, but I think that's the value add. And I think what you're saying is similar to that, that we're kind of breaking beyond the tools and saying, these are what we create with the tools. This is how you use your hands. And then these are what the tools are going to evolve into so that you're ready for those.
Yeah, one of the examples I like to talk about in the course is on the transition from like a drafting board to CAD models, 3D CAD models. That was a fundamental change. It wasn't you just kept doing things the same way you did them before, but the tool itself changed the methods or changed the way you thought about designing certain systems. I see a lot of the upcoming tools or the ideas around digital engineering or digital threads may lead to similar revelations in how we do some of the systems engineering activities at a more fundamental level, and that isn't just because of a specific tool, but more because there's a whole new fundamental way of interacting with how we do system development, system understanding, system design.